Here we comes to the example on page 7. We have Amy and Sophie on the merry-go-round, and it said that they complete 2 revolutions in 1 minute. So here is expressing the angular speed in 2 RPM, 2 revolutions per minute. So part A, we have to find the period of the motion. What is mean by periods? Periods means the time for 1 revolution. So if we have 2 revolutions per minute, how much time do we need in 1 revolution? You can do the calculation. Period is equals to 1/2 minutes per revolution. So 1/2 minutes, of course, we have to change it into standard unit. We are talking about 30 seconds per revolution. Okay, so this is the period of Amy and Sophie respectively. And so part B, we are going to find the angular speed. Angular speed is equals to 2 RPM. And we want to change this into the standard unit because RPM is not a SI unit. Firstly, we have to change the angle into radian. One revolution means 2 pi radian. So if we have 2 revolutions, that means 2 times 2 pi radian per minute. Of course, we still need to change the unit of time. We don't want minute, we want 1 second. So if 1 minute in 60 seconds, it completes 2 times 2 pi radian. Then in 1 second, it will have turned for 60th of the original amount. So this is the angular speed. We can simplify the expression into pi/15 radian per second. Part C. Merry-go-round runs for 15 seconds. Find the angular displacement. Now we have the angular speed, and then we have to calculate the theta. We can use the equation theta, angular displacement, equals omega t. Omega is pi/15 and t is 15 seconds. So cancel out, we have pi radian. Pi radian, or you can say it is half a circle, or 180 degrees. Okay, this is our normal way expressing an angle. So of course you can write it in pi radian as well. Part D, find the linear speed v. V is equals to r omega. Here, because Amy and Sophie are on different positions of the merry-go-round, Amy is at the outer rim 3 meters from the center, and Sophie is 2 meters from the center. So Amy is here and Sophie is here. 2 meters and 3 meters from the center respectively. But note that both of them are rotating with the same omega, but the radius are different. Amy is more outside than Sophie. So even if they are rotating with the same angular speed, that is how many degree angle per second, even the angular speed is the same, but the linear speed would not be the same. So we can apply this equation to Amy. So the linear speed of Amy will be equals to RA omega A. RA is 3. Omega A is pi/15. So we have cancel this. We have pi over 5 meter per second. And for Sophie, it will become Rs omega s. Rs is 2. Omega is the same. So we have 2 pi over 15 meter per second. Of course, we can change that into decimal number, okay, or you can express it in terms of pi. That doesn't matter. Part E, compare the angular speed omega and linear speed. For angular speed omega, for both Sophie and Amy, they are the same because they are rotating at the same angle per second. They are on the same roundabout, merry-go-round. So the angular speed is the same. Linear speed, for linear speed, the speed that Amy and Sophie is going, Amy will be larger than Sophie's speed. It is because Amy is at the outer rim, so the radius of Amy is larger than the radius of Sophie. So it have to move faster